Good afternoon. Welcome to one of the last two sessions of the conference. It's been quite a conference, a great one. I'm Kevin Boca from Boeing, and Tim O'Brien from Raytheon is my co-chair. Just want to welcome you and kick this off. Thank you.
All right, so I'll be doing the introductions for our folks, and our first presenter today is John Bucknell. He is the CEO and founder of Virtus Solis Technologies, a startup focused on deploying the first commercial space solar power platform. The floor is yours.
Thank you very much. I realized that my paper was placed in this session, and maybe it's not the best fit, but hopefully you all enjoy it. I will tell you, though, that even though I'm focused on solar energy, formerly I was in this vertical, and this is part of my continuing education requirements for my professional engineer's license. So again, the title of my paper is very long, so it has lots of keywords, so you can find it if you need to, but it's a derivative of a prior paper, which I'll talk about later, called Reactivity-Controlled Compounded Internal Combustion Engines. So that is a process by which you can achieve very high thermal efficiencies, and I disclose this for medium and heavy duty applications because it's good for megawatt and above shaft power. So I'm going to cover a few topics, talk about some background, talk about the details of the cycle, go through some analysis of a notional design, and then the implications of all that. So even though my intro didn't include it, I actually have been a combustion engineer for a very long time. I was the principal engineer for SpaceX's Raptor rocket engine 15 years ago. That architecture was all basically the same process. I went through this, and I've done 8 production engine programs across automotive and aerospace, and even complex hybrid solutions like the Zinger 21C, which is currently the highest specific output production certified emissions compliant engine on the market. So talking about motivation, about why I went to write this paper beyond the requirements to keep my PE. In general, in my 30 years of working in combustion, it's very hard to achieve the theoretical Carnot efficiencies for any thermal engine. And why can't we achieve them, and what's possible? So obviously there are ways to reduce the losses that these engines see, and there's also something we call exergy destruction. And if you're in the combustion world, you know that gases have thermal energy, which we call exergy, and if you isentropically expand it, for example, when your exhaust valve opens, that's destruction of potential energy you could have used for shaft work. So I'm doing all of those things in this particular article, and we'll talk about that. And then the other big thing is the combustion process itself, and how can you achieve much higher temperatures with the available combustion systems. And specifically, I'm using recuperation and advanced combustion to avoid the drawbacks of conventional combustion cycles. So I just put up the Carnot equation for typical temperature ratios that you might see in engines. You can see that theoretically amazing, oftentimes nowhere near that. And you'll see that in the chart a little bit later. But the basis of the reactivity control portion of the paper and the proposal is that if you work in combustion, the actual chemical kinetics of how combustion happens and its reaction rates are a little bit obscure. And so I actually compiled this chart out of a number of sources. But the actual combustion process, you end up with a liquid fuel or gaseous fuel, and you heat it up to a point, and then you get the actual combustion process and flame front starts after those initial conditions. And I would argue that actual combustion with the radiation at a flame front is actually driving all of these conditions to something very close to these temperatures that you see on this chart. If you're not familiar with the temperature ratio portion, you're actually looking at a reference temperature of 1,000 Kelvin divided by the actual. So hotter temperatures are to the left, and the ignition delay, which is the time it takes from a combustion bomb to when the flame front starts and the pressure rise, is an exponential scale on the y-axis. And you can see a whole bunch of common fuels that you might use, and you can see that they all have that same trend of exponential decay with temperature. So if you can get your combustion environment warm enough, you can basically have the ability to have combustion start as soon as your fuel exits or enters the chamber. So in that way, you can control the pressure rise or the heat release rate just by the rate of delivery of the fuel. And by doing so, you eliminate one of the larger challenges, at least in piston engines, which is the rate of heat release, which can induce mechanical shock and make the underlying components very, very high likelihood of breaking. And in fact, with the ability to do this, you get peak combustion pressures on the order of 350 bar, which means in a single stage you can get to 350 pressure ratio. So in the gas turbine world, that's quite high, right? So the first work I did on this topic was published in 2023. You can go find it. I self-published on ResearchGate if you're interested. I'll go through this architecture a little bit later, but what you need to know is that the recuperator, which is a heat exchanger on the backside of the combustion system, and a chiller or intercooler are used to control the absolute temperature entering the system. So I won't walk through what this architecture's got. I'll walk through the derivative that we're talking about today in a couple of slides. So as I said earlier, reactivity control is trying to control the temperature just before combustion starts, and we're trying to get to roughly 1,000 Kelvin. And in order to do that, at least for light loads and low overall pressure ratios, you need a recuperator to do that. So light load implies a recuperator, and then you're controlling the rate of heat release via injection rate, generally with a really high pressure ratio system. There are off-the-shelf heavy-duty injectors using piezo injectors for diesels that operate at about 2,700 bar, so very similar to what rocket combustors operate at. You also need an auxiliary ignition source for startability. And then in this case, we're talking about a compounded engine. So you have a piston engine as the topping cycle and a Brayton cycle as the bottoming. And these four-stroke cycles allow very high peak gas temperatures, 2,400 Kelvin roughly, using air as your oxidizer. But since it's intermittent, your structures can survive that. And then, again, operate relatively high pressure and high overall pressure ratios. And then the expansion ratio is quite high, but finite because of the geometry of the expander. And then we're putting a Brayton cycle both on the compressor side, raising the initial conditions going into the piston engine, and then expanding them out to ambient. And I'm limiting in this case to about 1,300 Kelvin, something that allows uncooled blades with known high nickel alloys. And the recuperator itself is very possible today with additive manufacturing and nickel alloys, such you can put it in 1,000 degree Kelvin exhaust stream. And last, these solutions are all operating at stoichiometry, such that the overall temperature is as high as you can get, and it also means the air consumption is relatively low for an air-breathing engine for an aircraft. And if you put a catalytic converter on the back of it, you can operate with the lowest tailpipe emissions, if that's of interest. So just for reference sake, I put together a list of shaft power, basically helicopter shaft power engines for interest on relative power levels, their relative dry masses, their power to weights, and their thermal efficiencies specifically, to show that most gas turbines that we're looking at are at least the ones that operate near sea level, are relatively low overall efficiency, and I'm targeting these two roughly megawatt power level systems as for the notional example for comparisons. If you follow diesel engines, the DOE's been sponsoring something called the Super Truck Program for the last 20 years, and they're demonstrating shaft thermal efficiency, so brake thermal efficiencies, around 55% with a lot of effort. And so that's state of the art, and that's the reference where this is coming from. But I'll tell you that diesel cycle alone struggles because it's running high diluent, so its absolute temperature is not very high, and they run really slow to operate with the injection schemes they have. So they don't fit well with Aero use cases because they are so heavy. These are 11 to 13 liter engines that often weigh two tons or more for a couple hundred kilowatts. So now I'll show you briefly the architecture that this analysis is paired with. So you can see there's a 6-cylinder piston combustor Shown here, there's 2 stages of compressor: a low pressure compressor, high pressure compressor. They're all both centrifugal stages. The first 2 run in parallel, so you can run across the large flow rate range of this operating engine, and then you have expanders, a core turbine that's expanding the combustion products of the piston cylinder, and then what I have is a bypass turbine I've added for extending the power range of the system. So you have a parallel combustor that operates separate power turbines, so that you can get high power levels for takeoff thrust or what have you, and then a recuperator downstream and a charge cooler to modulate the temperatures going into the piston cylinder device. As I said earlier, there's another paper in 2023, which is I will call the first generation solution on the left, and the Gen 2 solution on the right. These are relatively small engines in the grand scheme of things. This is a 1.5 liter 6-cylinder core engine, and then relatively small gas turbine on the other side. So 3 small compressors of about 100 millimeter in diameter, and then the expansion turbines are similar scale. But the interesting thing is that these systems are a couple hundred kilos, and one of the big differences between the first generation and second generation is the first generation had 2 bottoming cycles, one was Rankine, and that's a very heavy power recovery system. For aircraft engines, it's deleted on the second gen because it's not totally necessary, but I did include it in analysis. So what I'm showing here is a chart of comparison on the left, a couple of different variants of the system. So the green is the first gen solution, and you can see the specific power goes up almost to 750 kilowatts. And then the orange is the second gen, but the same hardware content. We're going from roughly 65% thermal efficiency to almost 72, and moving that power lower, or that efficiency lower in the operating regime, which is great for use cases where you're not operating at peak output. And then on the right, you can run these piston reciprocators at a number of mean piston speeds, relatively high for low number of hours of durability, and relatively slow for large durability. And I've shown the differences in output between the two. So the dark is the high speed and the light is the low speed. And you can see that 200 hours between overhaul, it gets you really high outputs, and then relatively low speeds gets you lots of hours, 10,000 hours between overhaul. So roughly 2 megawatts on the high speed system and about a megawatt in the low speed. Also, similarly, because of the bypass, you can run a lot of airflow at relatively low shaft speeds. You get very high output, not as good thermal efficiency, which you can see in these 2 charts here. The relative contributions, you can see that the gas turbine itself is actually extracting a lot of shaft power, and the secondary is adding quite a bit because its mass flow is so much higher. And similarly, you can see the specific air consumption for the compounded engine on the bottom is quite low, but you add a conventional gas turbine, the airflow is quite high. And then I'm showing here a pH diagram for those thermodynamicists in the room of how the energy is added and extracted. You can see there's a couple of compressor stages, and then the combustor is adding a lot of enthalpy at the top. The piston expander extracts most of it, and then the Brayton bottoming cycle expands the rest, with the recuperator transferring a little bit of energy. The recuperator is actually only moving a small fraction of the total, and allows it to be lower mass. So in conclusion, this cycle solves a lot of mission design challenges for shaft power in the megawatt range, with about 1/3 the fuel burn of comparable shaft engines, and has a really low air consumption, therefore low frontal area, relatively low installed mass, and very high thermal efficiency, and I think the highest anyone's ever reported. So with that, I'd be happy to take any questions.
That was really interesting.
Thank
I'm
you.
glad you were in our section.
Thank you.
Okay, floor is open to questions. We got about 4 or 5 minutes. Go ahead.
When you model, do you have losses for the piston component?
Yep, absolutely. Yeah, so
And that you're still showing like 70%.
that's indicated. Yeah. So just for comparison's sake, I show indicated. I don't show the break.
Right.
And the brake is harder to extract the losses on the piston cylinder side. So indicated is really easy to compare. So I don't model the friction losses very easily. This is a 0D model, so the friction is more difficult to analyze. So I try to just show indicated.
Do you suppose if you showed a brake or if you thought about losses, that it would change a lot? That's been
It's usually from a shaft power perspective, it's 3 to 4% of the available fuel usage ends up going to friction. So I would knock that number down by 3 to 4%.
Other questions? Here and in the back, go ahead.
Okay, mine is related to that. On the braking cycle side, what compression and expansion efficiencies do you use? And did you have pressure loss in the
Yeah, absolutely. So one of the great things about a lot of the reported gas turbine performance is they include the efficiencies or the losses in the efficiency number. So generally speaking, I'm using like 82 to 85% on the compressor and expander stages.
Are those state-of-the-art levels?
On the individual axial expander stages, sometimes they're as high as 94, but when you add 3 or 4 stages in a row, you end up down in the low 80s.
Yeah.
So it's easy to just look at state of the art and say, okay, well, let's not pick the best, but do a conservative estimate. But yeah, all those losses are included.
Yeah, that was the same question.
Oh, good questions then.
I've got one too, unless I don't want to. Okay, I saw something in there that said temperatures higher than material temperatures can operate at gas compression.
Correct.
Is that because it's a transient thing? Why?
Yeah. So conventional stoichiometric combustion in a piston engine usually peaks at around 2,500 Kelvin.
Yeah.
So that's not unusual. Rocket combustors run 3,500, but they're actively cooled with cryogenic propellant. So the fact that you're only running 2 to 3% of the time at that temperature allows you to operate the gas temperature much hotter than the walls.
Gotcha. That's what I assume. And one last one. What are the prospects of building this device?
Obviously, someone has to be interested to do so.
Why wouldn't someone be interested?
I would say that first of all, you have to get past the technical objections, right? A few of you are still skeptical, I can tell by the smiling. But if I would say, as a person that's built a lot of things, the shaft power use cases, primarily helicopters, frankly, there aren't very many of them, and the airframe manufacturers are very conservative. So it'd have to be someone like a Williams or a GE or somebody that's sure, absolutely. Heavy duty trucks, for example. But I will tell you they're all buying aeroderivative gas turbines. Like, they're not developing their own.
Well, what efficiencies?
These would be 3 times as efficient as a natural gas turbine that you're installed on the ground. So you'd have to convince whoever is currently manufacturing it to try something like this. It's a supply chain problem rather than a technical issue.
Do we have 1 more minute?
Oh, 2.
Where do you suppose that efficiency improvements come from? Is it looking at your diagram? It seems like it's because you're using more efficient compressor and expander piston once your volume is low.
Actually, I would argue that a large portion of the losses that you realize in internal combustion engines is that exergy loss, where your cylinder pressure is far higher than your ambient, and you expand that gas and you lose all the waste heat. So the fact that you can put a relatively high overall pressure ratio when the exhaust valve opens, you're still very high, and you can put expander stages behind it. So that's where a lot of the recovery is coming from. The recuperator also captures some of it, but that's more on the combustion side than it is on the thermal efficiency side.
Let's thank our speaker again.